This is example number 4, found on page 80 of our notes. I wanted to make sure that we cover an example about concavity. So our job is to find the concavity intervals and POIs if there are any. And we're going to do it for our same f of x that we have, which is 3x to the 4th minus 4x cubed minus 6x squared plus 12x plus 1. We know that in order to find critical points, we had to find the first derivative. So we found that f prime of x was equal to 12x cubed minus 12x squared minus 12x plus 12. In order to find intervals of concavity, we actually need the second derivative. So we need f double prime of x. That's going to give me 36x squared minus 24x minus 12. So what we want to do here is very similar to what we did before. We want to figure out when is f double prime of x equal to 0, or when does it not exist. And again, we would do our numerator, set it equal to 0, or get our denominator, and when it equals to 0, we'll know that it does not exist. Again, this is a quadratic or polynomial, so we know that it exists all the time because it's continuous all the time. So we just need to set when that is equal to 0. So when does that equal to 0? So now we get to use our factoring skills and realize everything is divisible by 12. So this is the same thing as 12, 3x squared minus 2x minus 1. Again, we're setting it equal to 0. We're going to factor. We find this to be 12, 3x plus 1, x minus 1. And then again, we're going to let the factors equal to 0. So when we do that, we're going to find x is equal to 1 or x is equal to a negative 1/3. Now what these do, these divide our interval, our domain, into concavity intervals. And again, we're going to use our concavity test, essentially the same, very similar to that of increasing, decreasing. But also, what we also find that these are also potential POIs. So first thing we did was to get our second derivative and set it equal to 0 to find these are not called critical points, but essentially we're finding our intervals for our concavity. So the second thing we're going to do is create a number line for our domain of negative infinity to infinity, and we're going to plot our points of interval for concavity. And then we're going to do the same thing that we did before. We're going to test some points. We're going to pick negative 1 to test. And we're going to pick x is equal to 0. And we're going to pick x is equal to 2. And we're going to test this in f double prime of x. So f double prime of x, where x is equal to negative 1. So we're just going to stick it in again. We're going to use the idea of using the factored form. So I would get 12. Plug in negative 1, I get negative 3 plus 1, it's negative 2. And this last one, I plug in negative 1 minus 1 is negative 2. So when I multiply this, I'm going to get a positive number. We can go ahead and multiply it out, and equals to positive 48, but we really don't care about that. All we really care is that this is a positive. So we do the same thing here. We're going to find f double prime of 0. So when we do that, I'm going to get 12. I'm going to plug in 0 here. I get 0 plus 1 is 1. Plug in 0 here. I get x. 0 minus 1 is a negative 1. And we can see that this is a negative number. And we do the same thing for f double prime of 2. So I get 12. I'll plug in 2. I get 6 plus 1 is 7. I plug in 2. 2 minus 1 is a positive 1. and I get a positive number. And again, we're only interested in whether it's positive or negative. So we have an interval from negative infinity to negative 1/3. We have from negative 1/3 to 1. And we have from 1 to positive infinity. Because of these pluses and minuses, we know our concavity. So for this to be positive, this is a concave up. So it looks like a U. For those are positive ones. If you have a negative concavity, that means like it's an upside down U or an N. So that's going to be for our negative one. And we can find the same thing over here. Since it's positive, it's concave up. So if we come back to our definition using our concavity, we know that if they're double prime, we plugged in our value and it was greater than 0, we had concave up. So positive is concave up. And if we had double derivative of f is negative, we had concave down. And notice if it was equal to 0, it means it's a possibility that it's a POI. So if you think about it, these values we found here are possible POIs, or points of inflection. And the way we find or determine points of inflection is right here, and there's asterisk that says if double prime changes signs, whether it's positive or negative or negative to positive, they have to change, at a particular x value, then we find that that point is a point of inflection. So if we look at what we have, we see that our concavity changes. So this point right here, so POI, we have a point of inflection at x is equal to a negative 1/3. We're going to plug that into f, so we got to go find f of negative 1/3. Notice we're going to put that into our original function, not f prime, that gives you slope, and not f double prime, that gives you concavity. So one of the points of inflection is at negative 1/3, comma, and I stuck it in my calculator and found negative 3.481. So that's our point of inflection. We found another one because it changes here when x is equal to 1. So another point of inflection is when x is equal to 1. So we got to go find f of 1. So our point is 1, 6. That's also a point of inflection. And that concludes this video.